In this recording, I'm going to go over an isomer checklist. So hopefully you've already watched all of our isomer videos and read the book. This is going to be one list that you'll want to refer to as you work on your isomer problems. So if you're given a chemical formula and you're asked if there are any isomers that are possible and you need to draw them, or if you're given a structure and you're asked to identify any isomers, you want to go through this list in order. The first isomer that we discussed in class was a coordination isomer. And to have a coordination isomer, so this will be the type, and this is what you need. So to have a coordination isomer, remember you're swapping a ligand that has a negative charge and a counterion that has a negative charge. So we need an anion ligand, for example, chloro, bromo, sulfato, and a counter anion. The second type of isomer that we have is a linkage isomer. And remember, a linkage isomer, this means you have one ligand, at least one ligand, that has two different donor atoms. And we only have a few of those ligands. So you'll look at your ligand checklist or the ligand list from our study guide, and you'll know that you have a ligand that can act as a linkage isomer if you're given two different names for that isomer. For example, CN minus on your ligand list can be either cyano if it's a C donor or isocyano if it's N donor. So the ligands that we need in order to have a linkage isomer: CN minus, SCN minus, NO2 minus, or OCN minus. So you need one of these ligands. The next type of isomer that we talked about was a geometric, which is one type cis trans. And you're going to see a variety of examples within your homework, and if you look on different videos online. And the ones that I'm going to test you on are specifically octahedral or square planar with exactly two identical ligands. So as you peruse different resources, you'll see other examples, especially when you get into organic chemistry. But for us in this chapter, I will test you. So on your exam 3 in the final, I will test you only on if you have two identical ligands. So 2 chloros, 2 bromos, 2 aquas, 2 amines. If you see a ligand that has a shape of octahedral or square planar and has exactly two of the same ligands, you know you need to draw cis and trans isomers. The next isomer we discuss, Fas-mer. And to have Fas-mer isomerism, you must have an octahedral shape with exactly 3 identical ligands. So I say exactly 3 because if you have 4, you do not have Fas-mer isomerism with an octahedral structure. You need to have 3 of the same exact ligand. The last type, we have optical isomers. And again, when you get into organic chemistry, or if you Google lots of different optical isomer videos, you'll see many examples out there. The 3 that I'm going to test you on that you'll also see in your homework, we will recap here. And these were also covered in the lecture videos. This is just a quick summary for you to use as you work on the workshop problems and your homework and study for exams. So we can have optical isomers if we have TD, a tetrahedral structure, and 4 different ligands. Octahedral structure and 3 bidentate ligands. As a reminder, a bidentate ligand is one ligand that has 2 donor atoms. So if we have 3 bidentate ligands, you actually have a coordination number of 6, which is where we get that octahedral shape. And the third type of optical isomer that I want you to know for our exams, octahedral shape with 2 bidentate ligands. And this must be in the cis position only. Again, because we have 2 of the exact same ligands in an octahedral shape. So that means we can have cis and trans isomers. As we saw in the videos, trans isomers are not optical, but the cis are. So hopefully this will help you as you go through your practice problems. What you'll want to do is you want to look at the chemical formula or the structure. If you're given the structure, write down the chemical formula and go through this list, every single one, to identify the different isomers. Oftentimes you have more than one type of isomer present.